Thank you very much, Dr. Collins. I think if it's all right with you, we'll hold questions until the two presentations have been completed. I want to welcome Assemblymember Quirk to the dais, and I was remiss earlier as Dr. Greenblatt is preparing to speak to thank two people who were very instrumental in making this hearing happen today. One of those sitting to my right is Gabrielle Meindl, who helps prepare these hearings for us every week. She has put a prodigious amount of energy into making this morning's hearing a success. And I want to thank you very much, Gabrielle, for all the effort. And my Chief of Staff, Sean McNeil, has also put a tremendous amount of time into making this happen. Thank you, Sean. I almost completely filled the gap there between presentations.
Thank you.
We'll
Oh, it's Control L. Control L. Yeah, okay.
Great.
All right.
Thank you. Dr. Greenblatt.
Thank you, Chairman Bloom and committee members. Yeah, it's my pleasure to present some of the work that myself and some of my colleagues have been doing here at Berkeley Lab. Over the last couple of years, I'm going to be talking not about climate change itself, but rather statewide policies to mitigate it through reductions of greenhouse gas emissions. And what you'll see is that this is one of the first studies to look at all of the policies that are both on the books being implemented as well as ones that the state are hoping to implement to see what the effects are on statewide greenhouse gas emission totals. Okay. So this is largely talking about results from a new model that was developed over the last couple of years that we call CalGAPS. CalGAPS is a comprehensive California energy and greenhouse gas accounting model, which, as I said, looks at all state policies that concern greenhouse gas emissions. It is divided into a number of sectors: passenger transportation, heavy-duty transportation, electricity generation, building energy use, agriculture and industrial energy use, and also emissions of sort of non-energy greenhouse gases like hydrofluorocarbons, methane, and so on. And the way we decided to look at this question of where greenhouse gases were going in the state is to group policies into three scenarios plus one at the end, which is essentially the do-nothing scenario, which we call S0. So we have S1 through S3 and then S0, which essentially turns off everything that's in the first scenario. There's a total of 49 discrete policies in all that cover all of the major energy-consuming sectors in the state: transportation, fuels, electricity, buildings, industry, and as well as non-energy greenhouse gas emissions, as I said. And the three policies are delineated as follows. So we have our first and kind of most important one, perhaps, what we call committed policies. These are all policies that are either underway or extremely likely to be implemented by 2020. There's about 13 policies included in this. Some of them are groupings of very similar policies, but most of them are discrete, such as the Pavley Vehicle Standards or the Renewable Portfolio Standard. And so that is what we consider kind of our baseline. Then on top of that, we have two other policies that build upon S1. So there's this uncommitted policies, S2, that add to what's in S1 other policies that may lack detailed implementation or financial plans to get there, but the state would still very much like to have happen. And so we've kind of considered those as optional or potential policies. Then finally, S3 combines the effects of S1 and S2 and adds some additional policies that are a little more speculative, that include existing policies where we've tuned up the knob. So, for instance, pushing the 33% RPS to a 51% RPS in this particular case. We extend the running of nuclear plants, for instance, is one other policy. There's about 15 more policies in there. And so this is more a question of if we could do everything we wanted, or many of the things we wanted, how much further could greenhouse gas emissions get? So that's S3. So you'll be seeing our results in terms of those three in the next couple of slides. The main results are really summarized in one graphic here. And so I'm going to walk through this kind of slowly and carefully so that you can digest all the information in here. What we see, first of all, are historical statewide greenhouse gas emissions according to the state inventory from 1990 up to about 2011, which is the last year that we had data at the time that this paper, which appeared earlier this year in Energy Policy, was published. In addition, the black line, then there's a dotted line, which goes out to the 2020 target, AB32, back to the 1990 level, and then continues in a straight line fashion to the 2050 80% reduction target. And in addition, which is set, of course, by executive order, in addition, there's a 2030 sort of potential target, which is consistent with what CARB had suggested, a kind of a percent and kind of a constant percentage reduction per year after 2020, which would be kind of a curved line that sort of goes through a 40% reduction in 2030. And we use that just as a reference point to ask sort of how good we're doing relative to that. But it's not an official it's not an official target. It's just a proposed one. So we see the four projections, S0 being the worst because we undo what we've already done, as I said, it's in red, and then S1 through S3 here. And I would say the first message is that obviously we don't want to be on S0 because emissions immediately go up and they keep growing through 2050. All of the policies that I've modeled here that have greenhouse gas reductions, the good news is that they all seem to be able to meet the 2020 target. So that's the first kind of conclusion, that even with the policies already in the various sectors for S1, the committed policies, we're very likely to be able to meet the 2020 target without additional policies. We will also have further reductions past 2020, but that's where the difference starts to become very visible here, that there are large additional reductions that happen if you add those policies in S2, and you roughly double the reductions again in S3. Staying with just the committed policies does not get you much below the 2020 target, and in fact, we see sort of a bottoming out around 2030, and then emissions statewide tend to go up again, and that's because essentially all the policies stop making improvements on a percentage basis or in absolute amounts, and because of population and economic growth, total emissions climb. You'll also notice that there are error bars on these, so we've done our best to estimate the uncertain parameters inherent in the model, and you see that this grows over time. The major contributions to this uncertainty band is population and gross domestic product, or state product, as I said. Also, our assumptions for how much building efficiency we're going to do plays a major role in this uncertainty too, but there's other parameters in there as well. Finally, in terms of, well, two more things. In terms of where we might get to by 2030, you can see that there is a huge range, more than a factor of 2 in statewide emissions in 2030, depending on which of these three scenarios you're on. And if you're able to implement everything in the S3 scenario, we could get below a 40% reduction, which is very encouraging. That said, it's not easy to get on this scenario. It's at the present time unlikely that we could implement everything in that, but many of the policies in there might be possible, and so that ought to be heartening. On the other hand, getting to our 80% target does not appear possible under even the most aggressive of these three scenarios, and that indicates that there are gaps in policy as well as technology that are going to need to be brought online in order to get us the rest of the way there. We can get a lot of the way toward this 2050 target, but we still end up in 2050 at roughly twice the intended target. So instead of 85 million metric tons of CO2 per year or so, we're at around 170, 180. Okay, so a lot of the way there, but not close enough. Now, one thing I wanted to show, that I was encouraged to show, and it is in the paper as an important sort of alternative view, is you notice how the emissions reductions, particularly the purple and green scenarios, fall well under this straight line in the early years. Well, that turns into a cumulative emissions picture, which essentially banks a lot of carbon credits if you're looking at instead of a target in a particular year, the total amount of CO2 emitted, say, between 2010 and 2050. That so-called carbon quota, as it's sometimes referred to, is actually more important for the atmosphere and for climate than instantaneous emissions in a particular year, because it's the total amount of CO2 that stays in the atmosphere which drives global warming. And so in this picture, we now show the integrated amounts of CO2 emitted under these four scenarios, plus this so-called straight line pathway, which is now no longer a straight line, but it's a curve, because, of course, emissions are decreasing year by year the further on we go. So this eventually approaches a flat line here. I've included a scaled U.S. scenario that was sort of developed by the International Energy Agency that sort of closely follows this, but that's not relevant for this discussion here. As you can see, the purple and green, the S2 and S3 scenarios, stay under this so-called straight line scenario well into the 2030s, and for the S3 scenario, it actually stays under it all the way to 2050 and probably a little bit beyond. And so if we're looking at cumulative emissions, these early reductions, even though they do not hit the 2050 target as articulated in the Schwarzenegger Executive Order of 2005, would still be very positive for climate. So it is an alternative view that might be worth bearing in mind as we set future state policy. Now, part of the power of doing this analysis and having individual greenhouse gas emission policies modeled is that we can look at the impact of individual policies on total statewide emission reductions. So what I show here, and it's a bit of an eye chart, but I just wanted to give you a flavor of what we've been able to do, is we took, for instance, the S1 scenario, all the committed policies, and then we systematically took away just single policies at a time and asked how much higher would emissions be if that was not present but everything else was. And we did this by decade and then sort of rank ordered it by the largest emissions change in any decade. And you can see that, so these are all 13 of the policies modeled in the S1 scenario. You can see that what rises to the top of the stack are the vehicle efficiency standards, the PAVLI standards, that reduce, or if they're removed, they would increase, but I think of it as a reduction. They reduce more than 20 million tons in 2020, and that accumulates to more than 40 million tons per year by 2050, implementation of these standards. So these are very important policy levers. They're among the strongest tools that we have. They could be increased and have even greater effect. And the other two sort of top three greenhouse gas policies listed here are the RPS standard and perhaps surprisingly the phase out of imported coal power, because coal is such a carbon intensive form of energy. But I do make a note here that while it may not count anymore in California's inventory, if those coal plants are still running, the power is sold elsewhere, the carbon is still going in the atmosphere, and so while it's not our statewide responsibility, it's still somebody's, so we need to think maybe carefully about whether this is actually improving things overall. You can see through a quick scan here the names of these policies, which are in more detail, of course, in the paper, that it cuts across a number of different sectors. We have the LCFS here. We have vehicle miles traveled reductions. We have reductions in high GWP or high global warming potential gases, which are mostly these hydrofluorocarbons used for refrigeration, and foam blowing for insulation and things like that. And down here we also have two policies that impinge on water, which I wanted to highlight given the recent drought announcements. We have a 20% water conservation standard that is in state law. This target is for 2020, and it targets urban, so residential and commercial water use, and saves on the order of 5 million tons of CO2 as well per year by implementing this. Also, the phase-out of once-through cooling plants that is in progress will save an additional several million tons and also would decrease use of water in the state. We also did this for the other scenarios, and I'll just briefly say, if we look at S2, there's some additional savings on top of the ones I just showed, which are also very important. Perhaps the most important next policy is the strategic plan for efficient buildings. And this one could, if implemented as we modeled, which is admittedly ambitious, could save as much as 50 million tons of CO2 per year. So a very significant amount, but the challenge there is in really implementing it to touch all existing buildings as well as very efficient standards for new buildings. There's also some additional water conservation that I just want to point out, an additional 26% according to some other legislation here. I think this is also a 2020 target, so it'd be nice if this were implemented in the next few years now, given where we are, but that also provides some greenhouse gas reduction relief. I just want to mention briefly that we have a paper in review looking at Governor Brown's recently announced 2030 policies that cover renewable electricity, reduced petroleum use, building efficiency, cleaner heating fuels, reductions in methane and other potent greenhouse gases, as well as land CO2 sequestration. And we've modeled all of these, and all I can say now, because it is in review, is that if all of these were implemented as he envisions, it would lead to very significant additional reductions below those that I modeled for the S1 scenario. So stay tuned for that. So this is really my last slide of content, and I wanted to spend a few minutes here because what I've done is try to think about all of the research questions and policy gaps that remain across the different sectors that I've modeled, areas where the state needs to spend more time in order to potentially reduce CO2 emissions, greenhouse gas emissions further. So I won't read everything, but I want to highlight several of these items, and feel free to ask me about any of these during the Q&A. So on transportation, we have a zero-emission vehicle policy, but there's questions of whether it's fast enough adoption or how we can get the number of zero-emission vehicles on the road out faster. Certainly, there are significant greenhouse gas savings from doing that. Another question on that topic is, could we improve vehicle efficiencies further beyond what was in the Pavley rule, with now the federal standard? There's certainly technical feasibility for doing that. I also think it's important to have the state look at some emerging trends such as potential vehicle automation or ride sharing, other strategies that might be able to reduce what's called VMT in the trade, vehicle miles traveled, so reducing the total use of vehicles. Do these have a significant bearing on the transportation sector greenhouse gas emissions? Many analysts feel that they would. And also what's relatively absent is focus on reductions in heavy truck greenhouse gas reductions. And one I want to call out, we don't have an airplane GHG policy. Part of that is because the amount of greenhouse gases emitted by airplanes that are counted in the state inventory is relatively small because so many flights happen out of state. And so official state inventory rules are to not count any flight that one endpoint is outside of California. So there's the question of, is that the right policy? Because the emissions are still happening. Is there a way that California could help to reduce greenhouse gas emissions for all air travel in and out of the state? Fuel supply. How can we improve the low-carbon fuel standard to, what I say, to maximize low-carbon biofuels? There's a growing concern that there is not enough biofuel available in state at any price. And if the rest of the country starts to rely heavily on biofuels, that may not be available nationally either. And so we have this problem of wanting to reduce our footprint for liquid transportation fuels, but may not be able to purchase enough, or have the biofuels themselves be low enough carbon overall because of the other what are called upstream emissions from producing those biofuels. And so this is a real issue that I think could have a strong bearing on how low our greenhouse gas emissions get, is what are we going to do about our transportation fuels? Also, hydrogen is kind of a sleeping policy. We know that hydrogen can be very low carbon. We know that the state has some support for hydrogen that's been consistent, but it doesn't seem to be playing a major role in our transportation solution right now. Should it play a larger role? How can we get there? Okay, I'm going to go through the rest of these quickly because I know I want to leave time for Q&A for both of us, but I think the other things to highlight here, we now have a detailed implementation plan for building efficiency, AB 758, but I think that there may be research and policy gaps that remain, and in any case, we want to carefully monitor how this is implemented to make sure that we're capturing the full amount of savings and understand how we can maximize our efficiency, because obviously up till now it's been challenging to get the full amount of efficiency that the state would like to with existing building efficiency upgrade programs. There's interest also in further savings from, say, doing building electrification of heating or solar-assisted heating. There are some opportunities that aren't really that don't exist as policy right now. I'm going to skip down to the bottom here, beyond energy, which are sort of these non-energy greenhouse gas emissions. There's increasing interest now of the state to look at reductions in methane and hydrochlorofluorocarbons. What we have found from our modeling, especially the modeling that I mentioned that's still in review, the emission savings from looking at these sources are very significant. And therefore, the state is wise to be spending time looking at all economic and technical opportunities for reducing this, because this would give us an enormous additional lever to reduce our overall greenhouse gas inventory, aside from everything we're doing in the energy space. And so I really urge the state to continue looking here and thinking of ways to maximize that potential. And I think another area that's kind of a sleeping giant is the use of land use carbon management. We have a lot of land that was historically forest that has been turned to rangeland that could be potentially carbonized, as it were, with tremendous greenhouse gas reduction benefits. There's other things we can do with other sorts of land that may also reduce the greenhouse gas footprint, and so that's an area that I think further research is needed. And finally, I wanted to mention that there are impacts on criteria pollutants from reducing our greenhouse gas emissions in the transportation sector. We have a separate set of standards, the EPA ozone standards, that are especially important in areas such as the South Coast Air Basin and the San Joaquin Valley. We think that the emissions of ozone precursors such as nitrogen oxides are going to exceed those standards under our current set of regulations, and so we need to do more there to bring that down. I know that the ARB is actively working to understand what else can be done technically to bring those air pollution emissions down, but it is very challenging to do so. So there's additional opportunities. So putting the flip side, there's additional opportunities for greenhouse gas reductions if we work together with those agencies looking at the pollution standards. So it could be a win-win. All right. Finally, just as a quick recap, we think that as a result of our modeling of existing policies that we're on track to meet the 2020 AB 32 target, and that there is a potential for much greater emissions savings by 2030, but it depends a lot on which pathway we take. Governor Brown's new announced policies will accelerate potentially significantly that 2030 reduction target. However, none of the policies that we have modeled here seem to be sufficient, even in combination, to meet the 2050 target, and we're off by still roughly a factor of 2. So we have a lot more work to do in order to get there. And I would say I was trying to think about, is there any research or policy hole specifically that I wanted to highlight as a final slide? And I really concluded that no, this is kind of, it looks like a laundry list, but really all of these are important in their own right, and I wouldn't call out any particular policies being especially important for the state to focus on. Really, all of these require a close look. They all have potentially large greenhouse gas reduction levers, and so I'd encourage your committee and the state overall to take a close look at all of them. And so with that, I'll stop and entertain your questions. Thank you.
Thank you, Dr. Greenblatt. I know Assemblymember Williams had a hand up earlier. Would you like to ask a question?
I was very interested in as much detail that you could provide on your S2 and S3 policies, particularly not just, I know when you do a slide, you have to sometimes illustrate what you do, but not how you do it. And I think that providing the committee members with that would be very useful, particularly also providing probably the committee members of UNC and Natural Resources would be very useful.
Sure. So I'll say first, the paper is publicly available, including detailed supplemental information, and I actually have it on a memory stick with me. I can direct you and the rest of the committee members to that. But I'm also happy to give you a couple of minutes of overview if that's what you would like now.
I would. Give us a little bit of detail on the S2 and S3 policies. That would be great.
Sure. Okay. So I have some backup slides that I prepared for that. Of course, right? We always come with an extra set. First, I just want to say, so I won't go through this, but I'll say, yes, we have a model structure that looks at all sectors. We essentially dictate how much the policies are going to change demand in different ways, and some of those demands interact, like the demand for electricity will in turn create a demand higher or lower for different kinds of fuels. And so all of that cascades through the model, ultimately resulting in emissions of greenhouse gases from fuels and then from sort of the non-fuel sources that I've mentioned a few times here, like methane from waste and so on. The model is all developed in a simple spreadsheet format, and we have a number of knobs that we can turn in order to simulate that as closely as possible what we think the impact of various policies are. Now, I'll say the way we implemented each policy, and these are all in interaction, which I think a hallmark of the model, that it isn't looking at just one policy without regard for any of the others, but we implement them together. So the effect of, say, decarbonizing the fuel supply will then have a magnifying effect if you're also doing efficiency reduction in fuel use somewhere else. So those two complement. In terms of what the S2 and S3 policies actually are, so I have these charts which kind of summarize what all of the actions are, and I think rather than reading them, let me just highlight a few for you. So S2, the major ones that were left out of the baseline or S1 scenario are the efficient building policy, which is the most significant greenhouse gas reduction strategy that I think of. And that's because it isn't clear exactly how this is going to be implemented. And at the time, there was less detail than there is now. So the idea in this one is we assume that every building, every existing building would be touched by 2050, and its efficiency would be increased to roughly, if I'm remembering correctly, 50% of 50% better efficiency, both in terms of natural gas and electricity, than it is sort of in the 2010 baseline. So over time, all of that gets baked in, which is why the emission savings are much larger in 2050 than in earlier years, because you're phasing in through the building stock. And of course, new buildings are also built much more efficiently than they are today, I think on the average of 60% more efficient. So those numbers can be debated, but that's how we model that kind of policy. We also have an explicit phase-out of all hydrofluorocarbon uses. So these, there is a model that estimates how much these are used throughout the state based on statewide air conditioning and refrigeration consumption and the estimated leakage from that. So we assume that over the next 35 years that these would essentially be phased out of the stock so that by 2050 there are no more emissions of those. And this is supported by kind of national policy now where there's a lot of interest in phasing this out over the next couple of decades. So the question is not whether it can be done, but how quickly it can be done, particularly in the early years. But we think that by 2050, that'll be possible. Let's see, what else is in here? So the zero net energy buildings is in S2. So all buildings that are touched are also, there's an amount of solar PV, in this case rooftop PV, which is added to offset the energy use from those buildings. So that makes a significant additional amount of renewable energy on the grid. We have some reductions in waste from landfills, which has a resulting reduction in greenhouse gas emissions. As I mentioned, there's additional water conservation. There is a relicensing of the Diablo Canyon nuclear plant, which I realize is controversial, but we wanted to see what the impact was. There's savings of about 8 million tons of CO2 per year for that. So not doing that, of course, would mean we have to make that up somewhere else. And we also have high-speed rail included in here, as well as some increases in combined heat and power plants, and the electricity storage target that was recently announced. It actually doesn't save you very much, but that's just a modest amount for starters. And then for S3, I would just say very quickly, we accelerate a number of these policies. We have a greater RPS target, so this 51% is actually very close to what the governor has recently announced as his target by 2030. We also assume that there would be further reductions in vehicle usage, so vehicle miles traveled. We model a U.S. policy produced by the U.S. PIRG and assume that that's applied statewide. So some of these are speculative. We say if this were to be implemented in California, this is what the resulting reduction in greenhouse gases would be. But I think to give other people a chance to ask questions, I'll stop there, and if you want to speak more later or over email, I'd be happy to do so.
Mr. Obernolte.
Thank you, Mr. Chair. I have a question for Dr. Collins. So was very interested when you were talking about how the reduction in snowpack in the Sierra was driven by the Pineapple Express storm tracks moving northwards. And I know that you were careful to say that we can't establish for certainty that that's being caused by increased global temperatures, but I'm interested in the suspected mechanic by which those temperatures would be moving those storm tracks. Can you talk a little bit about that?
Right. So as you warm the planet, one of the things that changes, and the reason why the storms are affected, is that the whole structure of the climate system is being altered. The poles, actually, both the North Pole and the South Pole, are getting appreciably hotter than land further south. And so you're altering. One of the major drivers for the circulation in the climate system is the difference between the very hot tropics and the very cold poles. That's a very basic driver in the climate system. That difference between the hot tropics and the poles is being reduced because the poles, Alaska, Antarctica, are heating much more rapidly than land to the further south. And that, combined with some other factors, are literally moving the circulation system around. So this alteration in the large-scale circulation of the atmosphere is following because you are altering the basic structure of the temperatures that we've historically enjoyed.
Okay, thank you. So how close do you think we are to being able to say definitively and scientifically, yes, these two are definitely causal?
I think we're at this movement of the storm tracks falls out of very basic theory. It also falls out of the climate models. Climate models, I think, actually predicted it before it was observed. So this is a pretty direct consequence of global warming. It's one of those things like higher moisture in the atmosphere that follows directly out of pretty basic physics of the climate system. It was predicted analytically before it was observed from satellite, and a colleague of mine up at the University of Washington first observed it from satellite. But yeah, we now know that this is occurring, and it's a consequence of global warming. So what the thing that's a little tricky right now is the reason why I wasn't able to give a crisper message about the consequences of this for the state of California is that while the climate models all say, yes, it's moving northward, at the moment some of them have the storm track positioned too far south, some of them have positioned too far north. And if you look at sort of the net effect from averaging all the climate models together, you get what amounts to a bit of a coin toss. We're quite confident, though, that regions that are quite further north, like Canada, will get wetter, and regions that are much further south, like Mexico and Central America, are going to get appreciably drier.
Okay, thank you. And my second question, I don't know who is more appropriate to take this, but I'm interested in your opinion of the degree to which climate change is anthropogenic. So Dr. Collins, you talked about the effects of climate change on our water supply, and Dr. Greenblatt, you talked about the effects of human activity on global greenhouse gas emissions. And so I'm interested in your opinion of how tightly those two are linked. Are we causing 100% of this? Are we causing some of it, and some of it's naturally caused? What's your current thinking on that?
Let me take a crack at this initially, because this is my area of my personal research is in the causative agents for global warming. So it is true, and if you go to the Grand Canyon, you can see a beautiful record of natural climate change that goes back 500 million years, right? So we know that climate change has occurred naturally in the past, and we know we know that climate has changed here in California, again, due to natural causes. So let's fast forward up to the present, and there are two, on time scales of decades to centuries, there are two quick actors of natural climate change. One of them are volcanoes. So the Pinatubo eruption that went off in the 1990s eliminated half of the warming that occurred since pre-industrial times. So the climate had warmed by roughly 3/4 of a degree centigrade relative to pre-industrial times. Pinatubo canceled half of that over a 3-year period. So that's a fast actor. It put up this big screen of sulfate aerosols in the stratosphere, reflected sunlight back to space, acted sort of like a screen parasol over the whole Earth. Second fast actor is the sun. So the sun, for example, caused what's known as the Little Ice Age that occurred in the 17th century. You can see this in paintings all over Europe, people skating on the Thames, people skating on rivers all over Europe that were frozen solid. The sun went quiet, and that caused and this was observed by Galileo and his colleagues, and this caused a cooling of the climate system. Those can both act quite quickly. We actually have very good data on both of those. Neither of them explain what we're seeing now. There's a clear fingerprint of mankind's signature that cannot be explained anywhere else, and the physics of this clearly points to greenhouse gases, and that is that the lower atmosphere is warming, the stratosphere is cooling. There's no way you get that from volcanoes, no way to get that from the sun. The only way to get it is by changing greenhouse gases. We also know, thanks to very good chemical evidence, that the increase in carbon dioxide in the Earth's atmosphere is man-made. How do we know that? Because there's a signature of the carbon source and its isotopic composition. This is sort of the weight of the carbon that's in carbon dioxide. Plants favor light carbon. That decays away, and you get a completely different there's a different isotopic signature of fossil fuel emissions. What we're seeing in the Earth's atmosphere is a clear fingerprint that the increased carbon dioxide is from fossil fuel emissions, and also a clear fingerprint because the lower atmosphere is warming, upper atmosphere is cooling, that the warming is due to greenhouse gases. This is evidence that has not been, the isotopic evidence has not been challenged. So, very quick answer to your question, but as far as we know, and we know a lot, most of the warming that we're seeing now is man-made. And we can, of course, there's still skeptics who are contending that this is not the case. They have not yet been able to deal a serious blow to this dipole issue that I mentioned to you about warmer surface, cooler stratosphere, and the isotopic evidence is also uncontested, and that's a very clear fingerprint that the carbon dioxide is coming from fossil fuels, no other source, and it's not from volcanoes either. That's another, little ringer in the deck, but that the emissions from volcanoes are orders of magnitude lower than man-made emissions of CO2. Okay. So, bottom line, sorry for that very rapid data dump on you, but the conclusion of the data dump is that we are very confident that mankind is causing the global warming that we're seeing now.
Thank you. That's exactly what I was asking.